Hello, good afternoon. I am Jigar Ratnottar from Atmiya Engineering College, Rajkot. Today we are going to solve the GTU question paper of the year January 2012. Let's start with the paper. The first question, that is the question number A, that state Ohm's law and its limitation, 4 marks. B, state and explain the Faraday's law of electromagnetic induction, 6 marks. And state the Coulomb's law and discuss the factors which affect the law, that is 4 marks. So the question 1 contains almost the Ohm's law, Faraday's law and Coulomb's law, all the laws. Now start with the Ohm's law. George Simon Ohm, the scientist, find out one of the great law of the electronics engineering, that is the Ohm's law, that gives the relation between the current, voltage and the resistor. So he proves that the equation I equals to V by R, where the I is current measured in ampere, V is the voltage measured in volts, whereas the R is the resistance measured in ohms. What exactly the Ohm's law said? Whenever the potential difference V applied to any current carrying conductor, that is again it is almost a conductor like a metal, etc., anything, iron, anything, and it has some resistance, that is R, then whatever the current passing through that material is I, that is directly proportional to the potential difference V applied to that material, and it is inversely proportional to the resistance which is offered by that material. So we can say that I is directly proportional to the V, whereas it is inversely proportional to the R. Ohm's law is also useful when among these 3 quantities any 2 quantities is given, then you can easily find out the third one, like that from table, that the first equation, that is I equals to V by R, where you given the current, where you have to find out that the I, so it must be known the value of V and the R. Now the next one, if you are aware from the value of the I and the resistance R, then you can easily find out the V from the equation V equals to I into R, where your voltage or your potential difference is the product of your current and the resistance of that material. The next one, that is R equals to V by I. For that you have to sure about the value of voltage and the current. So by using the equation R equals to V by I, you can easily find out the resistance offered by that material whenever the voltage and the current passing through the device. So this is very important law of electronics. The Ohm law says whenever the voltage across a resistor is proportional to the current I that flows through it. So in general the resistance does not depend on the voltage, but the basic law concerning the flow of electricity, that is Ohm's law. So that law is directly belongs to the electricity. Here given one example where you can easily find out the Ohm's law, the equation, that is V equals to I into R, where at the left hand side we see the battery that has the potential V. The next one, there is a current I measured from the battery, and the next one is a bulb that contains some resistor, that is R. So you can see that our V equals to I into R. So whatever the voltage produced by the battery, that is equivalent to the product of the current passing through it and the resistance offered by that bulb. So that's why it is proven that V equals to I into R. Now just go through one video where you can easily find out the Ohm's law. Okay, the next topic, Faraday law of electromagnetic induction. This phenomena is called the electromagnetic induction. Faraday's law directly concern about the electromagnetic induction, whereas the Ohm's law concern about the electricity. It is described by the Faraday's law. Write the Faraday's law like that. E of t equals to minus d phi of t by dt, but the phi is a flux. In order to understand the Faraday's law, we need to understand the concept of magnetic flux, that is a phi. Because the Faraday law directly belongs to the electromagnetic induction, that is the magnetic material. Write the definition of the magnetic flux, that is the phi m, again it is a magnetic flux, equals to integration of B electricity and it is a dot product and it is in the vector form. That's why you can see the vector sign over the B and the dA. So phi m equals to integration of B dot dA. According to the figure, where you can see that one material, magnetic material that has the two poles, north pole and the south pole. Whenever passing through, whenever it keeps some distance with the conducting material which has the electric field density, that is the B, some of the magnetic lines passing from north to south, you can see. So whenever we are just moving that magnetic material near to that conducting material, that is a metal or anything conductor, then the flux is generated in that material, because whenever the magnetic lines are cut, the magnetic flux is produced. Now we see that the magnetic flux is exactly like the electric flux. We studied in the Gauss's law. The flux is defined in terms of a vector area, as we already know that B and dot dA. So describe the magnitude and the direction of this vector. This is a vector quantity, so you have to mention the arrow. Now just go through one video. Before that, we see that the magnitude is common area and the direction is normal to that area. Here you can see that the arrow with the, which is exactly define the normal area to the direction of the passing through the magnetic lines, that is the dA.
Hi there, it's David Williams again from Okanagan College, and talking some more about electromagnetism. And in particular today, what I want to talk about is Faraday's law, which is named after Michael Faraday, one of the earlier experimenters in electricity and magnetism. And we have a picture of him here. And it was for Michael Faraday that the farad was named, the unit of capacitance. And it took me a long time to figure out where the farad was named, or who it was named after, and it was only a couple of years ago actually that I figured that out. Now, I'm not going to tell you what Faraday's law is yet. I'm going to show you a couple of animated experiments. Now, this is from the PhET webpage, and you can find all sorts of great physics animations and science animations on the PhET webpage. And this one in particular is demonstrating Faraday's laws, and this one's called Faraday's Electromagnetic Lab. Let's see if I got that site here. I do actually. So I'll bring that down. Here's the website for Faraday's Law Lab, Faraday's Electromagnetic Lab. So you can take that website down and check it out yourself and play around with it. It's kind of interesting to play with it and see what kind of different effects you can get. Anyway, let's go back to the actual lab itself. So what we've got here is a permanent magnet with north and south, and we can see the magnetic field that's created from that magnet around in the screen here. And inside the magnet we've got a loop of wire to which a light bulb is attached. Now, here is a demonstration of Faraday's law. And what you'll notice is I move the magnet and the light turns on. And in particular, when I move the magnet, notice what's happening with the magnetic field. It's changing. So Faraday's law says that if you have a changing magnetic field, that is going to induce a voltage. in this case we've got a completed circuit, so it's going to induce a current in the circuit, and that light bulb is going to turn on. Here's something else that's kind of interesting. Okay, I've got 3 loops currently, and I've got it's off the screen, but I can change the number of loops. Change it to 2, change it to 1, and look at the light bulb as I change this. I'm going to change it now, and you'll notice that the light bulb turns on as I change the number of loops we have. And also, if I change the area, you'll notice the light bulb turns on just very briefly, very dimly, as I change the area that the magnetic field, the area that the magnetic field passes through. So the basic fundamental underlying equation for Faraday's law is this. If you have a
Flux fiber.
Changing magnetic field, that is going to induce a voltage. And in particular, it's a changing flux with respect to time. So the induced voltage is going to be equal to the rate of change of the flux with respect to time times how many loops you have. Another way to write this, if you remember what flux is, and we actually write flux in terms of flux density. So flux is going to be equal to flux density times area. So N times the flux density times area is equal to flux. So what you can see from this equation here is if you have a changing magnetic field, you'll induce a voltage, or if you have a changing area, you'll induce a voltage, or if you have both. We can go back to the magnetic Faraday's law and see here's the changing magnetic field induces a voltage that creates a current, or let me shift this over a little bit.
So according to that video, we can easily see that we can easily see that whenever the magnetic material, which is the north pole and the south pole, kept near to the any conducting material which are somewhere around the poles, and you can see you can observe the bulb. Whenever the magnetic materials is kept distance between that conducting material, then the bulb will not glow. But whenever you are kept near to that magnetic material into that conducting material, then the bulb is exactly glow. So this is the electromagnetic induction we can see from the Faraday's law. Now the next one is the Coulomb's law. Coulomb's law almost state about the two forces, different polarity forces applied to any material. Then what exactly the result that is observed from the Coulomb's law. Now start the Coulomb's law. It gives the force of the attraction or the repulsion. Either the two charges attract with each other. Whenever the different polarity materials are kept near, then they are attract with each other, which has the polarity positive and the negative. But if the same polarity charges are kept near to each other, like positive or negative, then they are repulsed with each other. They both are opposed to each other. So if 2 point charges like the Q1 and the Q2 are separated by some distance, that is r, then the magnitude of the force of repulsion of attraction between them is given by the Coulomb's law equation, that is F is a force which is applied to that two charges. So F is proportional to the Q1 and Q2, and it is inversely proportional to the r square. So if we remove that proportional, then we have to keep one constant over there, and that is a Boltzmann constant, that is K. So overall equation becomes that F equals to K into Q1 Q2 by r square. That is the equation of Coulomb's law, where Q1 is a one charge, point charge of that material, Q2 is again another point charge of another material, and that materials are difference with the some distance, that is r.
Coulomb's law. This fundamental law of electrical science is also referred as inverse square law. According to this law, if two charged bodies are kept at a certain distance, they will experience an attractive or repulsive force depending upon the nature of their charges. If the bodies are charged by similar electrical charge, they will repel each other. If the bodies are charged by opposite electrical charge, they will attract each other. Suppose one body is positively charged with plus Q1 and the other body is negatively charged with minus Q2. The force acting between them is attractive. Again, one body is positively charged with plus Q1 and other body is positively charged with plus Q2. The force acting between them is repulsive. Again, one body is negatively charged with minus Q1 and other body is negatively charged with minus Q2. The force acting between them is again repulsive. The force is a vector quantity, which means it has direction in addition to its magnitude. Here the force acts along the straight line joining the centers of the charged bodies. Now, if you increase the charge Q1 keeping Q2 unchanged, the force is obviously increased. If you decrease the charge Q1 keeping Q2 unchanged, the force is obviously decreased. Similarly, if you increase the charge Q2 keeping Q1 unchanged, the force between them is again increased. If you decrease the charge Q2 keeping Q1 unchanged, the force is obviously decreased. According to Coulomb's law, force F between them is directly proportional to either Q1 or Q2, or in other words, F is proportional to the product of Q1 and Q2. Now, by keeping their charge fixed at Q1 and Q2, if we bring the charged bodies nearer to each other, the force between them increases. And if we take them away from each other, the force between them decreases. If the distance between their centers is r, it can be proved that force acting on them is inversely proportional